Hello everyone, welcome to the video number 5 of this video lecture series on understanding FEA concepts with 1D example. Okay, so previously we have seen FEA algebraic equation using solid mechanics, right? So we have got something like this: 1 minus 1 minus 1 1. Okay, this is a stiffness matrix for 1D bar element, and these are algebraic equation. Okay. Force vector is equal to element stiffness matrix into displacement vector of element. Okay, and this we have said subject to boundary conditions. You okay, not this one. This is a generic form. Okay, so this is what we have got. Okay, so from this lecture onwards, for next I think 5 to 6 lectures, we will derive algebraic equations using FEA method. Okay, using FEM. So we'll derive this same equation, okay, these same equations, but using FEM method. So let's get started. So first I will just give overview of the steps that are needed to derive the FE algebraic equation. Okay, so first we will have strong form. So first we will just see the steps. Okay, later we will see all the steps in detail one by one. Okay, so what is this strong form? This is a partial differential equation. Okay, so this is nothing but governing equation for structure solid mechanics or structural mechanics. So this is a governing equation that defines the behavior uh, or deformation of structural member. Once we have strong form, okay, uh, we get something called weighted residual form. Weighted residual form, and this is also differential form. Once we have this, we get weak form. So we'll see this how to get all these forms one by one in detail. From weak form, we get approximate form. So here we introduce the concept called shape functions or approximate functions, and that's how weak form will become approximate form, and then we solve this form of equation. So in order to get these equations using FEM, we need to follow all this process. Okay, so we'll see this in detail one by one. Okay, okay, so let's start with a strong form. Okay, so in this particular video I'm just going to derive the strong form, and then we will stop. We'll continue from next lecture. So strong form. Okay, before this I just want to say it is very important that we do not ignore the conceptual understanding, okay, using 1D example. Okay, so 1D example, because with 1D example only we can understand the concepts very easily. Okay, if you directly try to understand with 2D or 3D, it will be very difficult. You will not be able to have clear understanding uh, of physical significance behind those equations. Okay, so we'll try to focus more with 1D example. Even with 1D example, we'll not go to generic form of 1D example, 1D element. We'll try to use the simplest form of 1D. Okay, so that is what I wanted to say. Okay, let's see the strong form. Okay, and as I said, I will take a simple example. So I'll take the rod subjected to axial force. Okay, so let's take this is a axial force Q0. Okay, it's a uniform bearing load. Q0 is nothing but it's a Newton per mm. Okay, and the length is L. Okay, this end is fixed. Okay, so we'll try to derive a strong form for this particular problem. Okay, so before for that what I will do, I'll want to uh, explain you something. Okay, let's take no, let's cut the section here. Okay, and I will make it into two pieces. This particular rod I will split it into two pieces. Okay, if I take this particular section, both sections are same, right? Because it is just cut. Okay, virtually I have cut. So under the application of this external force, okay, I will get some internal force, right? So at this particular section, the internal force is going to be F, right? And obviously it is going to be something like this. Okay, so it is going to be in equilibrium. This particular section is in equilibrium, right? Both are same section, so they are going to be in so it is in equilibrium. So we can say this section uh, for this member will have F, and this section for this right hand side member will have opposite force F, so that they are in equilibrium. Okay, so F is nothing but internal forces. Okay, internal forces. Okay, so with this understanding, let's continue. Okay, so what next? Uh, so we will no, take one infinitesimal section here. Okay, let's take this is the infinitesimal section. Why I'm taking infinitesimal section? Because I want to derive the partial differential equation, right? So let's take this section of length dx. Okay, and we'll write the internal forces for this section. This is going to be F. Okay, and this is going to be F plus df, right? So you can understand from this. Okay, for example, you can just imagine this particular rod. Okay, if I take this particular section, okay, it is going to experience the maximum force, right? Because this particular section uh, will experience the force from the right hand side of the section, complete structure, right? If I take this section, this will have less force compared to this section. So this will have less force. Okay, and that force will be experienced from this particular forces. Okay, and if I similarly take for example this section, okay, this section will have even less force. Okay, because it is going to experience only this much of for external force. Okay, so that way we can say if this section is F, this particular section will have force with the increment of uh, df. Okay, so df can be anything, positive or negative. In this particular example, df is going to be negative. Okay, so we can say F plus df. And how it came also, you can say here, for example, this section, if I say f, this section is going to be f plus df, right? And if I just move this boundary and make it move it to here, okay, I can say I get this one, right? So it is nothing but f on left hand side, f plus df on right hand side. So these are the internal forces. Okay, so with this we will write the equilibrium of forces using solid mechanics. Okay, sigma f is equal to 0. Okay, so we will say internal forces, okay, plus external forces are equal to 0. Okay, they are in equilibrium for this section. Okay, so let's write for this section. So internal forces are nothing but f plus df. Okay, so I will just say this is the x coordinate. Okay, this is x equal to 0, and this is x equal to l. So this is right hand side is the positive direction. So f plus df minus, because in negative f is opposite to f plus df, so f plus df minus f, this is internal force. Now plus external force. So what is external force? So external force is nothing but q0, which is newton per mm. I can say external force on this section dx is going to be q0 dx, right? Newton per mm into mm, which is nothing but newton, okay, is equal to 0. Further, if I simplify this, uh, df, okay, plus q0 dx equal to 0. So df by dx plus q0 equal to 0. Okay, now I now want to uh, I'm interested in deformation, right? Structural behavior in terms of deformation. So I will put substitute f in terms of u. So for that I have to first write f in terms of u. So f is nothing but internal force. F is equal to stress into area. Okay, internal stress. Sigma is equal to nothing but E epsilon and A. So we can say A E epsilon is nothing but du by dx. Okay, so du by dx is nothing but deformation gradient. Okay, or we can say derivative of u with respect to space or coordinate. So this is nothing but strain. Okay, so I'll just substitute this value here. Okay, so I get d by dx A du by dx plus q0 equal to 0. Okay, and I can say du by dx del square u by d square u by dx square A plus q0 equal to 0. Okay, so I can write it in terms of u double dash plus q0 by A equal to 0. So this is my strong form. Okay, this is a strong form. Okay, so we have got the strong form. Okay, this one. Okay, and the next one is a weighted residual form. So before going to the weighted residual form and coming to this approximate form, okay, we will derive, which is approximate form is nothing but FEA equations. Finally we will get here. Okay, so before going to FEM, okay, what we'll do, we'll try to find the analytical solution for this strong form. Okay, so that in future when we get FEA solution, okay, we will compare it with our analytical solution. Okay, So I'll say analytical, okay, analytical solution to our strong form. Okay, so I'll say u double dash plus q0 by ae is equal to 0. Okay, so in order to get a solution u, I have to integrate this, right? Integrate with x. So integrating the u double dash, I'll get u dash plus this constant integration will become q0 by ae to x is equal to c1, right? Further integration, I get u plus q0 a x square by 2, okay, is equal to c1x plus c2. Okay, so these are two equations I have. And uh, now I will just now we want to find the solution, so obviously we need to apply the boundary conditions. Okay, so what are our boundary condition? One end is fixed, so u at 0 equal to 0, and u x equal to l is equal to u dash at x equal to l is equal to 0. Okay, this is our boundary conditions. So as I said, no, this member is going to experience zero force. Okay, ideally zero force, that means u a a sorry, so ae f is equal to 0. F is nothing but ae du by dx. Okay, since this is end of the road, so x equal to l equal to 0, so we can say u dash at l equal to 0, right? This is same, both are same. So these are two boundary, u dash at l equal to 0 and u at 0 is equal to 0. So these are our boundary conditions. So I will just put here uh, subject to boundary conditions, u of 0 equal to 0, u dash l equal to 0. Okay, so I'll put these values boundary conditions in equation 1 and 2. Okay, so u at 0 equal to 0, in putting it in equation 2, I get 0 plus 0 is equal to c1 of 0 plus c2, so I get c2 equal to 0. Okay, u dash this I will put it in equation 1, so I get 0 plus x equal to l, q0 ae l is equal to c1. So this c1 is nothing but q0 by ae l. Okay, so what is my solution u? I'll just substitute this in our the equation 2. Okay, so what I get, u plus q0 equation 2. Okay, q0 by a x square by 2 is equal to c1x. So c1 is nothing but this one, so q0l by a to x plus c2 is equal to 0. Okay, so 0. So u is equal to minus 1 half x square, okay, q0 by a, okay, plus x q0 l by a. So this is our analytical solution. So I want to just plot this equation. Okay, displacement with respect to length of the rod, that is x. So I will just, what I'll do, as I said, no, we'll try to simplify as much as possible. Okay, so this solution, this complete process from uh, here to last, I will just try to simplify it further. Okay, so for plot purpose, okay, so I will just say simplify. Okay, so what we'll do, we'll say q0 equal to 1. Okay, let's check unit load. We will also say a is equal to 1. Okay, that means q0, sorry, not 0 but 1. Okay, that means q0 by a is equal to 1. And we will also assume that unit length of the rod. Okay, unit length rod, that means L equal to 1. Okay, so what is my differential equation here? Okay, so if I just put it here, so it will become u double dash plus 1 equal to 0, subject to boundary conditions u of 0 equal to 0 and L equal to 1. So I will say u dash at x equal to 1 equal to 0. Okay, and if I just put just solve for this, okay, my solution will be, I'll just put it here. Okay, u solution, or I will say u of x. Okay, this will become 0. This term is also 0. q0 is 1, sorry, not 0, 1. q0 by a equal to 1, and this term is also 1. Okay, so I will say u is equal to minus 1 half x square plus x. So this will be very easy to plot. Okay, we can plot this also, but this is very easy. Okay, and further I think we'll be using this form only. Okay, this most simplified one for deriving our FEA equations. Okay, so let's plot this. Okay, we want to plot the solution. This is my x, this is u. Okay, x is the length of the rod, so we have assumed that it is x equal to 1. Okay, unit length of the rod. So if I say x equal to 0 here, so displacement is 0. So this is one point. If I put x equal to 1 here, so u at 1 is equal to minus 1 by 2 plus 1, which is nothing but 1 by 2. So at x equal to 1, displacement is going to be 1 by 2. Okay, so these are the 2 points I have got. Okay, uh, so the solution will be something like this. Okay, why? Because as we know, at u dash 1 equal to 0, okay, that means this derivative is, the slope is 0. Okay, so we have taken the slope here, u dash 1, which is a 0. Okay, so this is our solution, which is nothing but uh, minus 1 half x square plus x. Okay, okay, so this is our solution. Let's just try to understand. Okay, further this solution, we know this is our length of the rod. This is our length of the rod, x equal to 1. Okay, this is a force. As you can see, this here the displacement is 0, and here we get the maximum displacement, right? So if I say u is equal to 0 here, here u is equal to max. Okay, which is nothing but 1 by 2. And if I say u dash or force is equal to, here will be a max. Okay, because if you see here the slope is the maximum, so here we get the max force. Sorry, so this is correct. U dash is equal to max. U dash is nothing but force. We know internal force is nothing but AE U dash, right? AE du by dx. So we can say U dash is nothing but force only, internal force, which is going to be max at this constraint. And force here, U dash is going to be a 0, right? Because U dash is equal to 0, so force equal to, internal force is going to be a 0 here. And so you can also like understand this physical significance when we are pulling this rod, okay, from this end. Okay, we can imagine that this particular section is going to experience maximum internal force, right? Because it is impacted by this complete rod length. If I take this section as I explained earlier, this is going to experience only, let's say if this is half, this is going to experience only half of the rod force. Okay, and similarly here it is going to be a zero because it is not going to experience any force. Okay, so internal force at this location is zero. Okay, and if you, I think I am sure that you would have done FEA analysis mostly, right? Cantilever beam problem is the first way that we do, okay, in our FEA career. If you apply some force, you would have seen at this constraint end, okay, you get the maximum stress. Stress is nothing but internal it is due to internal force. So here you get the maximum force, sorry, maximum stress, and here you get the maximum displacement. Okay, here you we don't get no zero stress. Okay, because we are no, we would have done in FEA the 3D analysis. Okay, and there are so many other factors coming to that. There will be, here we are just talking about 1 degree of freedom. Okay, it's a 3D, so there will be a no shear forces, shear stresses, so those will be there here. So you won't say zero stress, but we can say the minimum stress will be reported at this end. Okay, and maximum will be reported at this end. Okay, and with this I think hope this why it happens, you can clearly understand from this our analytical solution. Okay, so with this no, I'll just quickly summarize what we have done. Okay, we have previously we have got few algebraic equations using solid mechanics, and these equations we want to achieve using FEM method. Okay, so we are in that process, and we have explained the steps for achieving that. Okay, and these are the steps: strong form, weighted residual form, weak form, and approximate form. Okay, and in this particular lecture uh, we have seen the strong form. Okay, we have seen strong form, partial differential equation, and analytical solution for that. In upcoming lectures maybe it might need a 3 to 4 or maybe 5 lectures, okay, to explain all these steps. So once no in future when we are at this stage, okay, we would have got the FEA equations using FEM method. So why we did no, today, why we not talked about analytical, because when we are here we want to compare these results with our analytical solution. We want to compare with analytical solution. Okay, so that is the reason we have tried to get analytical solution, and you can remember this, or in future just will take the reference of this solution. Okay, analytical. Okay, so see you in next lecture. Okay, we'll in next lecture we will see weighted residual form, and probably we will also see weak form. Okay, so thank you very much.